Hello everyone. Having figured out how heat moves through a green roof system, through the vegetation, the planting media, the roof deck, I actually spend most of my time looking at how that affects the entire building. How heat moves through the envelope, through the windows, through the walls, uh, and through the ground, through the floors. And also what kind of heat gets generated inside. And that makes a big difference. Ultimately, it's all about how it affects the mechanical system. It's all very complicated, and that's why it costs a bit for an energy model for LEED certification or what have you. What I'm going to do for the next few minutes is to try and simplify it and focus on the roof system and how a green roof, what kind of impact the green roof will have on the entire building. Now, there's a lot of ideas, advice. I rarely come across an engineer who does not have their own idea on how a green roof works, its impact on a building, whether they're effective or if they're not effective. And it does. It depends on where you are, how you're using the building, what the building does when you do your energy model, if you're going to see any difference at all. And I understand all that. And I do understand it is not one size fits all, that is a bad way to look at it, and that we need to be very smart about how we look at building energy these days. So I'm going to spend the next few minutes going into a little bit more detail and hopefully make it a little bit clearer about how to take a first look at a green roof and what kind of building is really going to benefit from that. So let's dive in and take a look.
What I'm doing here is taking what can be a complicated analysis and breaking it up into three categories: mission, how a building is used; climate, where the building is; and construction, how is it built. First, let's look at mission. And I have to admit, I was looking for a word that started with an M because it worked well with my cute title of E equals MC squared. But once I selected that word, I realized it really is pretty good at describing what is probably the biggest aspect of what you're paying in your utility bills each month. So with mission, we're talking about the purpose of the building, which affects the general design, but it also describes what happens inside the building. How many people are in it? How is it lit? What kind of equipment do you have? Is this an office building or is it a factory? And the people and the equipment and the lights, they all generate heat, and you have to deal with that heat. Now, engineers like to refer to the equipment sometimes as plug load. You plug something in, not only do you have to deal with the electricity that's being used, but you also have to deal with that heat. And also the schedules. It's pretty critical as to when you're generating this heat and when you're using the electricity. Again, looking at an office building, right in the middle of the day, when the sun is beating down on the building and through the windows, you are also have the most people in the building and you're using the most equipment. So that affects how you're going to set up your mechanical system and how much you're going to pay for electricity. Now, you could have a different type of building that operates not during office hours and during other times, maybe at night, say a restaurant or an event space, or maybe on weekends like a church. So in those situations, you're going to deal with how and when you're using your electricity and energy inside the building is going to be a little bit different. Next is climate. Where in the world is this building? Is it in the desert? Is it in a rainforest? Is it in a cold climate, a warm climate? Is it a coastal climate? These are broad categories of types of climates that a building would have to deal with. But we need to look a little bit closer, say what we call a microclimate. The example of this would be in the San Francisco Bay Area, where you can be in a cool, misty beach and then drive an hour inland and you're in a hot, dry valley. So this gives you a better idea of what types of temperature you deal with, humidity, and then we look even closer at what I call the nanoclimate. What do you have right around the building? Is it shaded? What kind of wind does it have to deal with? Wind is an interesting one. It may be dealing with what is called urban canyon effect, where you can be walking down the street and not feel much wind at all and go around the corner and get blown away by a 30-mile-an-hour wind. Well, that wind not only affects the people walking down the street, but it does affect the buildings on either side of that street, which is funneling that wind. So that all needs to be dealt with. Finally, we have construction. The building size and shape is a big determining factor on whether or not you're going to see any energy savings with a green roof. Here I refer to the roof-to-wall ratio, or the area of a roof to the area of the walls. And let's say we look at a skyscraper where this ratio is really small. In dealing with the environment and the sunlight hitting the building and things like that, the roof just doesn't have nearly as much of an impact as what you do with the windows and the walls. On the other hand, you may have just the opposite situation, a building that is only 1 or 2 stories but covers 100,000 square feet. In that case, the roof is a big part of how you deal with the environment, especially the sun hitting the building. You also have to look at the interior. Inside the building, how is the design, what is the design of how the space is broken up? And what are you doing directly underneath the roof? So is this a type of space where it's very open and there's really nothing between the people and the roof system except some air? Or do you have an attic space or some type of plenum or something like that where you have air moving through it, or especially if it's ventilated, how efficiently it's ventilated? And that will affect how much of an impact the roof has on the rest of the, on how the building deals with heat and how much energy it's using. And ultimately, we're talking about the mechanical system. This is really what you're paying for. You talk about the environment affecting the building. Primarily, we're talking about the comfort level inside the building, or ultimately the temperature control. So if we're trying to maintain temperature, whether it's because of people or the type of equipment we have in there, to maintain that temperature, we have to have the mechanical system designed properly for it. And if it's not designed properly, if it's inefficient, then we're going to be spending money on the electricity for that as well. Now we get down to the nitty-gritty, the fundamentals. The first law of thermodynamics. It's one of my favorites. It's also often called an energy balance, mainly because it's a simple concept. The heat going in, including heat generated inside, has to equal the heat going out. So, for instance, we're looking at a building here, and this is a cathedral in Milan, and on a hot day, sunny day, we have the building being heated up by the sun, by the ambient heat or the surrounding hot air that's heating the building as well as getting inside the building. And in this case, we have a big, massive structure where some of that heat can get stored in the structure itself instead of constantly heating up the people inside the building. And the surface of this cathedral is also radiating heat to the sky, just like everything else on the surface of planet Earth, that even though you may have the sun radiating on the building, it's also releasing that heat through radiation to the sky at the same time. Sounds kind of crazy, but it's the way it works. And in fact, this is a critical survival mechanism for plants, where they're absorbing sunlight, which they need, but they also have to get rid of the excess sunlight. And one of the ways they do that is by radiating it back out to the sky. Or we may have a cold night where we have just the opposite situation where you're just losing heat everywhere, and you may need to turn on your heat inside the building, or in addition to that, getting some of that heat back from the building structure. Now, all of this can be complicated by what we call transients. Things can change over time. And here we're looking at a hot day and a cold night. It could be 80 degrees during the day, and it could get down to the 50s at night, which is certainly happens in Milan. And that can complicate the analysis and how we deal with heat, and especially in a massive building. It can be beneficial, but it still makes it a little bit difficult to look at. And these transients are not just, say, over a 24-hour cycle, but can also be seasonal. All Earlier I mentioned some of the ways in which energy is used in a building, and I'd like to revisit some of those. I talked about the lights and equipment using a lot of electricity in a building, and in fact they can make up a really big percentage of the total energy use in the building each month. Take, for instance, a data center, which is going to be the computers alone and the cooling systems for the computers can be 95% of the utility bill for that facility each month. Now, by themselves, the electricity usage cannot be affected by a green roof. A green roof is only going to be dealing with the environmental issues as to how much heat is going into or going out of the building. The electricity being used inside the building is not affected by a green roof. But, as I mentioned, they do create heat. Now, dealing with the heat in the building, that's where the green roof can come in. Ventilation was another one. There's also situations where fan energy can be a large percentage of a building, say in a laboratory or an auditorium, something like that. And fan energy, the power required to run a fan, is intimately tied to the heating and air conditioning. Because when you run a fan, not only is the fan using electricity, but again, the heat generated from that tends to heat up the air. So even though you may be using the fan to help cool a space, you have to deal with the extra heat from the fan. Again, it gets complicated, but you do have to know how to deal with this stuff when you're doing the analysis. In the case of our discussion, as long as you're aware that this is something that really plays a factor when you're saying, well, boy, how come our green roof didn't give us as much energy savings as we thought? These are the types of things that have to be taken into account. Ultimately, what we're trying to do, as I mentioned, is minimize the amount of energy that we spend heating and air conditioning a building. There are different ways to describe how you're saving energy. In engineering, we often use absolute energy savings, kilowatt hours per year or per month, the amount of energy used per square foot. These are all terms for describing the efficiency of a building, of the building design, of the equipment in the building. And some of these are highly dependent on the building size. So if you're saying we're going to use so much energy per month, obviously a bigger building is going to use more energy per month. On the other hand, if you were looking at how much energy you're using per square foot, there we're not looking at the building size, we're looking at how the building is being used. So those are terms that are a little bit more, maybe a little bit more technical. On the other hand, we can be looking at percent energy savings, and this is used quite a bit, and is probably the one that is the easiest to think in terms of, sort of get our brains around. And we can actually break that down into a couple different ways to look at of the whole building, which means let's say if you put up a green roof and you see a difference in how much energy you're using and you want to describe that savings, you can have that savings in relationship to the whole building, how it's operating, what's happening inside the building, or you can look at the savings for just the air conditioning and heating. So as I said, that's really what we're dealing with when we put up a green roof. Or we can look at the bottom line. How much money are we saving? And this gets us looking at it a little bit differently, because then it's not just the energy, the cost of the electricity or the natural gas, but it also looks at the equipment. And in certain climates, this is really important. In a mild climate, you may not use your air conditioning or heating all that much, and by using a very clever strategy, including green roofs, you may be able to cut the size of your air conditioning in half or eliminate it altogether. So the capital costs are a big aspect of when you're describing how much you're saving and you get down to the dollar savings. You need to look at the capital as well as the energy. But that's the more straightforward part of looking at how a green roof might save energy. What gets a little bit more dicey is when we say, well, it's saving energy compared to what? Compared to what you're doing to the building, but more specifically, compared to what you're doing to the roof. Now, the two most popular or likely things you're going to do with a roof, especially most directly related to comparing it to a green roof, would be solar PV panels and cool roofs. And in this case, let's look at solar PV panels. Now, they both deal with sunlight. We're both mostly concerned with what happens during the daytime when the sun is hitting the building. Now, a solar PV panel, it's pretty straightforward that they're collecting that solar energy and converting it to electricity for use in the building. Very active kind of device. Whereas the green roofs are more preventive. They're simply just trying to keep the heat out of the building, or depending on the time of year and what's happening, keeping the building a little bit warmer. At night, obviously the PV panels are no longer active, whereas the green roof remains active. So the foliage, which really is active all the time, dealing with the environment, using all the mechanisms that nature gives it to remain near the outside temperatures at all times. So in that sense, you could think of it as definitely being active. And also, in the rest of the green roof system, there's some mass there. It's able to store some heat. Just like in that cathedral, you can store some heat in a green roof. And at night, when that heat is being released, it's being released not just to the outside of the building, but can also be transferring from the system to the inside of the building. Again, with cool roofs, they both deal with sunlight primarily. That's what we're mostly concerned about. Cool roofs reflect most of the sunlight, but not all of it. It's not good to think of a cool roof as something that simply reflects away all of the sunlight. It doesn't work that way. On the other hand, green roofs really do reflect or transfer or use all of the sunlight. In other words, what a green roof is not using for making the plants grow, it's getting rid of all the excess heat. It's just how vegetation works. That's how it survives. They're also both still active at night. Cool roofs will continue to emit heat at night, no matter what, at pretty much the same rate, whereas the green roof foliage does adjust itself. So where a cool roof can get cooler than the surrounding air temperature at night, the green roof foliage will adjust itself. Now, in a hot climate, this can be a good thing, and why sometimes a cool roof under certain circumstances may be preferred over a green roof. But in most climates, it usually doesn't quite work that way. You really need to look at each individual case and decide which is going to be best for your roof. But for the most part, a green roof is going to outperform a cool roof, especially when we look at seasons. If you're in a part of the world where you do have seasons, that cool roof is going to just keep emitting heat off of that roof all the time, no matter what. Whereas green roofs can adjust. The plants go dormant. They're no longer dealing with the sunlight, as I mentioned earlier, where it can reflect it and transfer it to the air because it's gone dormant. It's sitting there, it's dried up, or it goes away depending on what you have planted up there. And in fact, it can actually absorb more sunlight. It can actually help heat the roof a little bit in cold climates. Okay, now that we've covered some of the how and why, we can take a more intelligent look at what buildings are the worst candidates for a green roof And what are the best? Let's start with the worst. And I'm going to do this by category as we start out with by mission. Obviously, if you don't care about what the temperature is inside the building, then you don't really care what's happening with the building envelope. And if you don't care about what's happening with the building envelope, you don't care what's happening with the roof or what's on it, whether it's a green roof or not. And from an energy standpoint, obviously there are other reasons for doing something with an envelope and having a green roof. But from an energy standpoint, if you don't care about the temperature inside, you're not going to care so much about what's happening on the outside. And as I mentioned about ventilation, if you have significant exhaust in the building, if you're moving a lot of air through the building all the time, you can have a little bit of an effect from what you do with the building envelope, but not very much. So in laboratories, in many manufacturing facilities, they have to have very high exhaust rates. They're moving a lot of fresh air through these buildings. And you can adjust that so that you are able to negate an awful lot of what's happening with the roof. Climate. If you're in a cold, cloudy climate, for instance, Rochester, New York, which is where this photo is taken, you are not really dealing with sunlight a whole lot. You may be dealing with seasons, but for the most part, you're so busy trying to just get heat into the building that having a green roof may give you a little bit of a benefit, but not much. It's going to be very, very minor. And construction. This is a very tall building. And just by looking at it, in fact, I believe this is a approximately 50-story building, 50-some story building. And if you look at the top, that area of the roof is a very small percentage compared to the rest of the walls. So you're going to get a very small percentage savings from the roof. Also, if you have a bad mechanical design. Again, if the whole idea is to use as little energy heating and air conditioning a building as possible, if you have a very inefficient mechanical design, then you're going to be spending a lot more money on heating and air conditioning the building, and then what you do with the roof is simply not going to have as great of an impact. Now we can talk about our best candidate for a green roof. And again, I've used the three categories to help guide us through this part of the discussion. With mission, the most important part here is whether or not you're having to maintain a very tight range of temperatures inside the building. If you have critical temperature requirements, you need every tool possible for maintaining that environment inside. So if you're having to deal with heat outside, the sunlight hitting the building, the envelope becomes that much more important. And also how much air you're moving through the building. If you're not moving very much air through the building, again, most of the heat is getting in through the envelope, through the conduction, the heat conducting through the building envelope. And if the roof is a big percentage of the total envelope area, then how much heat moves through that roof becomes that much more critical. Regarding climate, a warm, dry climate is going to provide the best opportunity because you're not having to just spend a good part of a good part of the year heating the building. So if you can take advantage of a fairly mild climate where passive measures have a greater impact on energy savings, then what you do with the roof is going to have a bigger impact. So if you're not spending all your energy trying to heat the building and you're not in such a severe environment that you just simply have to run air conditioning no matter what, but you're able to take advantage of what you do with the building envelope, that is ideal. And again, when we look at the nanoclimate, if a building is shaded, you're not going to get much benefit from what you do with the roof. In fact, it's going to be difficult to use the roof to your advantage. On the other hand, the shading helps. Planting trees around a building is really probably the best thing you can do for keeping heat out off of the roof as well as the walls of a building. And construction. We talked about the dimensions of a building being important. So if you have a low building with, and here I'm referring to a large footprint. So these buildings that we're looking at in this picture, each one of them has a fairly large footprint, and they're only 1 or 2 stories. So these are the kinds of situations where what you do with the roof can have the greatest impact on how much energy you're having to use inside the building. If you ask me, will a green roof save my building energy? The correct answer is, it depends. Every building is different. Every building situation is different. In my experience doing energy modeling of buildings, I've often seen that small differences in how a building is used, where it is, how it's constructed, can make a big difference in the final energy usage, how much you're paying each month for your utility bills. So depending on the situation where you are, what you do to the envelope, how you set up your mechanical system, you need to be very careful in how you do that and in seeing how that impacts the relative benefit of a green roof. Also, local codes can hurt or help. They're intended to help, especially where you have required high R values in the walls or in the roof. Okay, so if you have a very high R value insulation in the roof, you may actually be trapping heat in the building, and you're not going to see much savings from what you see above that insulation. And that's a situation you won't see all the time, but it is something to consider. And also ventilation requirements. You have a laboratory or something similar where you're spending so much of your energy just moving this air around that you don't see much from what you do up on the roof, then that's going to have an impact. And also the green roof design. A thin, extensive system is not going to provide the same type of performance as a really deep, intensive system. And obviously, how much of the roof you cover will also make a big difference. If you want to get a number describing your savings, if you want to quantify those savings, you really need to do an energy model, a proper one that looks at the roof as part of the entire building. You need to look at the entire building because all these aspects of the building, the envelope, how the building is being used, the mechanical system, the schedules, all interact. So the only way you can really find this out is by doing the calculations. And the most widely recognized software for doing this are the ones based on DO2. I believe the most popular of these types of programs is eQuest. And eQuest doesn't do a bad job of giving you an overall idea of what's happening with the building, but it does have some limitations. For a deep, intensive system, a heavy system, it simply can't do that calculation. It just, you get an error message, and it just simply won't calculate such a heavy wall. It also can't model air moving through a building. So if air moving from one room to another or throughout a large room, that airflow cannot be modeled properly if it winds up being important in what happens in conjunction with the rest of the building and possibly the roof above it. Same thing with stratification. An atrium is not going to be modeled very well because it can't deal with the differences in temperature between the floor and the ceiling. You also have to be realistic with how you model it. You're comparing, as I mentioned earlier, you're comparing a green roof to what? So when you're doing the calculations, you need to be careful about what the comparison really is. You also need to be realistic with the temperatures. If the temperatures are fairly critical, and let's say for an office building, you're going to say that the thermostat is going to be set at 78 degrees, but in reality it's going to be set at 74, you may wind up seeing a savings that is unrealistically great. And same thing goes for other features of the building. So let's say, for instance, you would plan on using external shades in this building. You have to make sure you're really using it and really using it on the schedule that you say you are. If you wind up not using it, you may wind up with a different kind of savings, a different set of numbers than what you intended before you even built the building. And last but not least, don't believe marketing numbers. If it says save as much as, those numbers are most likely wrong. Those are really bad numbers to look at at all, and they really should be ignored. So if you're fortunate enough to be working with a best candidate position for a green roof, then you can start being more creative with what you do with the building envelope. As I mentioned, it's not impossible to have the opportunity to use passive measures with the building design to the extent that you can get rid of your air conditioning. Now granted, this is usually in very mild climates, but there are a lot of buildings in mild climates. So you can start using things like natural ventilation and again, being very creative with what fans you may need to have no matter what. But these are the situations where a green roof transitions from having energy benefits to having a comfort benefit, to being able to keep the building more comfortable. The most important thing is to identify these kinds of buildings and get some plants on top of them.
So there you have it. The answer that nobody ever really wants to hear, it depends, unfortunately is reality. Every building is a little bit different. Every building situation is a little bit different. How a building is used, where it's located, and how it's built. So how much energy you're going to be able to save by having a green roof up there is going to depend on these factors that we just went through. And not every building is going to get a huge amount of savings from a green roof. In fact, some are going to see a very small amount of savings, but a green roof never hurts, and that's a good thing to keep in mind. Now, there are a whole mess of buildings out there that would get a significant savings from having a green roof on top of it. What we need to do is identify those buildings and be smart about it and to do it correctly. But the main thing is, let's identify those buildings and let's get some plants on top of them.